Salamat! Mekeni! Tukika! Allow me to guide you in learning the different concepts and skills in Mathematics 9. I am Teacher Andrew, your soulmate. Do you know a friend who used to work or is still working while studying? And out of curiosity, did you ask how much your friend earned or earns? And at your age, were you enticed to look for a job to earn as much? Say your friend who is still studying while working gets paid 80 pesos per hour. If your friend works for 40 hours, how much will he or she get paid? Did I hear you say, basic sir? Pretty easy to compute, huh? We will simply multiply 80 pesos by 40. So, your friend should get paid 3,200 pesos. Now, say your friend has worked for X hours. How much will he or she get paid? Got attacked by X sickness? Don't panic. The procedure is still the same. We will just multiply 80 pesos by X. This means he or she gets paid 80x pesos. We soon realize that the amount he or she gets paid depends on the number of hours he or she works for. This situation can be modeled using a function. Recall that a function is a relation where no two distinct ordered pairs have the same abscissa or x-coordinate. The function can be described by the equation f of x equals 80x, where x refers to the number of hours your friend works for. The variable x is called the independent variable. Suppose y is equal to f of x refers to the amount your friend gets paid for. Then, y is called the dependent variable. So, when x is equal to 40, the value of the function f at 40, denoted by f of 40, must be equal to 80 times 40, which is equal to 3,200. For the x, the rule of the correspondence is a polynomial of degree 1. This means that the function f of x equals 80x is a linear function. And this you must have learned when you were in grade 8. Another real-life situation that can be modeled by a function is this. The area A of a room whose width is 5 meters more than its length. We assume that the room is rectangular in shape and thus its area A is equal to the product of its length L and its width W. Now, the width is given to be 5 meters more than its length. Hence, we have the equation W is equal to L plus 5. In terms of the length L, we may express the area A of the room by the equation A is equal to L times the binomial L plus 5. Expressing the area A, which is in square meters, as a function of the length L, which is in meters, we have the equation A of L is equal to L times the binomial L plus 5. In this function, L is the independent variable, while A of L is the dependent variable. Say the length L is 7 meters. What should be the area A of the room? By substituting the value of L in the rule of the correspondence, we have A of 7 is equal to 7 times the quantity 7 plus 5, which must be equal to 7 times 12, and the result is 84. The area of the room is 84 square meters. The rule of the correspondence, which is L times the binomial L plus 5, can be expressed as the binomial L squared plus 5L when distributive property of multiplication is applied. Hence, the function a of L can be rewritten as a of L is equal to L squared plus 5L. Clearly, the rule of the correspondence is a polynomial of degree 2. Hence, the function is not linear but quadratic. A quadratic function is a function of the form f of x is equal to ax squared plus bx plus c, or y is equal to ax squared plus bx plus c, where a, b, and c are real numbers and a is not equal to 0. Furthermore, the dependent variable f of x can also be represented as the variable y, where y is expressed in terms of the independent variable x. Let us identify which among the following is a quadratic function. Number 1, y is equal to the negative of the product of the binomials x plus 1 and x plus 3. We can see here that y is already expressed in terms of x. If we get the negative of the product of the two binomials as the rule suggests, then y must be equal to the negative of x squared minus 4x minus 3. And the highest exponent of x is 2. So the equation is a quadratic function. Number 2, y is equal to 5 times the binomial x minus 4. Y is already expressed in terms of x. 5 times the binomial x minus 4 is equal to 5x minus 4, a polynomial of degree 1. Hence, the equation is not a quadratic function. Number 3, y is equal to 2x times the binomial x minus 3. Y is already expressed in terms of x, and 2x times the binomial x minus 3 is equal to 2x squared minus 6x, which is of degree 2. Hence, the equation is a quadratic function. Number 4, y is equal to 6x squared plus 2x cubed plus 10. Y is already expressed in terms of x. The highest exponent of the variable x is 3. Hence, the equation is not a quadratic function. Number 5, y is equal to 15 plus 9x plus 3x. Y is already expressed in terms of x. Combining the similar terms, y must be equal to 12x plus 15, another polynomial of degree 1. Hence, the equation is not a quadratic function. Number 6, binomial x plus 9 times binomial x minus 2 is equal to y minus x squared. Y is not expressed yet in terms of x. Multiplying the binomials on the left side, the equation becomes x squared plus 7x minus 18 equals y minus x squared. Now, we have to eliminate the term negative x squared on the right side to isolate the variable y. We do this by increasing both sides by x squared. The resulting equation is 2x squared plus 7x minus 18 equals y. The highest exponent of the variable x is 2. Thus, the equation is a quadratic function. Number 7, y minus 7x to the 4th power minus 2x cubed plus x squared equals 0. Here, just like in equation number 6, y is not yet expressed in terms of x, but by inspection, we can already see that the highest exponent of x is not 2, but 4. Hence, the equation is not a quadratic function. So, it must be much clearer now that a function is quadratic when the rule of the correspondence is a polynomial of degree 2. At this point, let's have another real-life situation that can be modeled using a quadratic function. And here it is. A rectangular parcel of land is to be enclosed with 64 meters of fencing materials. Our task is to, part A, express the area of this parcel as function of its width. Part B, use this function to find the area of the rectangular parcel of land for each of the following values of the width. W equals 1 meter, W equals 2 meters, W equals 3 meters, W equals 4 meters, and W equals 5 meters. Since 64 meters of fencing materials is required to enclose the rectangular parcel of land, this means that the distance around it, or its perimeter, is 64 meters. Recall that the perimeter P of rectangle is obtained by getting twice the sum of the length L and the width W. So, it means that twice the sum of the length and the width of the parcel of land is equal to 64 meters. It follows then that the sum of the length and the width is 32 meters. Expressing the length L in terms of the width W, L must be equal to 32 minus W. Area A of rectangle is equal to the product of the length L and width W. Replacing L with 32 minus W, we can express the area A of the rectangular parcel of land as a function of the width W. So we have A of W is equal to the binomial 32 minus W times W, which can be rewritten as A of W equals 32W minus W squared. And this is the quadratic function that models the situation. Let us now find the area of the parcel of land for the values of the width indicated in the item B. We organize our answers by constructing a table of values. The table should look like this. This shall signify that the value of A of W, which is in square meters, shall depend on the value of W, which is in meters, used in the rule of correspondence. Let us now determine the value of the function A of W at each value of W. When W is equal to 1, A of 1 is equal to 32 times 1 minus 1 squared. Therefore, A of 1 must be equal to 32 minus 1, and the result is 31. Hence, when the width is 1 meter, the parcel of land has an area of 31 square meters. When W is equal to 2, A of 2 is equal to 32 times 2 minus 2 squared. Therefore, A of 2 is equal to 64 minus 4, and the result is 60. Hence, when the width is 2 meters, the parcel of land has an area of 60 square meters. When W is equal to 3, A of 3 must be equal to 32 times 3 minus 3 squared. And therefore, A of 3 must be equal to 96 minus 9, and the result is 87. Hence, when the width is 3 meters, the parcel of land has an area of 87 square meters. When W is equal to 4, A of 4 must be equal to 32 times 4 minus 4 squared. And therefore, A of 4 must be equal to 128 minus 16 is equal to 112. Hence, when the width is 4 meters, the parcel of land has an area of 112 square meters. When W is equal to 5, A of 5 must be equal to 32 times 5 minus 5 squared. And therefore, A of 5 is equal to 160 minus 25. And this results to 135. Hence, when the width is 5 meters, the parcel of land has an area of 135 square meters. Let's have another example. Mama Emilita has 360 feet of fencing materials to enclose 2 adjacent rectangular corrals for her pigs. The 2 corrals are equal in length and in width. The length is represented by the variable y, while the width is represented by the variable x. Let's write the total area A of the corrals in square feet as a function of the width x of each corral, that is, in feet. Since the corrals are enclosed using 360 feet of fencing materials, we have the equation 4x plus 3y equals 360. We then express y in terms of x since the function we are to write is in terms of x. 3y must be equal to 360 minus 4x. Dividing both sides by 3, y must be equal to 120 minus 4/3 of x. To get the total area of the corrals, we have to multiply 2x by y. Written as a function of the width x, the area A is expressed as A of x is equal to 2x times the binomial 120 minus 4/3 of x. Multiplying the quantities on the right side, A of x must be equal to 240x minus 8/3 of x squared. At this point, let us determine the total area of the corrals at each given value of x. You may use a calculator. We shall record our answers in this table. When x is equal to 35, A of 35 is equal to 240 times 35 minus 8/3 of the square of 35. A of 35 must be equal to 8,400 minus 9,800 over 3. And therefore, A of 35 is equal to 5,133 and 1/3. Hence, when the width of each corral is 35 feet, the total area of the corrals is 5,133 and 1/3 square feet. When x is 40, A of 40 must be equal to 240 times 40 minus 8/3 of the square of 40. A of 40 must be equal to 9,600 minus 12,800 over 3. And therefore, A of 40 is equal to 5,333 and 1/3. Hence, when the width of each corral is 40 feet, the total area of the corrals is 5,333 and 1/3 square feet. When x is 45, A of 45 is equal to 240 times 45 minus 8/3 of the square of 45. A of 45 must be equal to 10,800 minus 5,400. This means that A of 45 is equal to 5,400. Hence, when the width of each corral is 45 feet, the total area of the corrals is 5,400 square feet. When x is 50, A of 50 is equal to 240 times 50 minus 8/3 of the square of 50. And therefore, A of 50 is equal to 12,000 minus 20,000 over 3. And the result is A of 50 is equal to 5,333 and 1/3. Hence, when the width of each corral is 50 feet, the total area of the corrals is 5,333 and 1/3 square feet. And when x is 55, A of 55 must be equal to 240 times 55 minus 8/3 of the square of 55. A of 55 is equal to 13,200 minus 24,200 over 3. And the result is A of 55 is equal to 5,133 and 1/3. Hence, when the width of each corral is 55 feet, the total area of the corrals is 5,133 and 1/3 square feet. Kagamath, ready your paper and pen. It's Math the Moment! Model the given situation using a quadratic function. Mr. Santos wants to enclose the rectangular parking lot beside his house by putting a wire fence on the 3 sides. The total length of the wire is 80 meters. Refer to the figure. Express the area A as a function of width W. You have 60 seconds. Go! And time is up. Let the width of the parking lot be W and the length be L. Hence, W plus L is equal to 80, or 2W plus L is equal to 80. Expressing L in terms of W, L is equal to 80 minus 2W. Therefore, the area A as a function of width W can be expressed as A of W equals binomial 80 minus 2W times W, which can be rewritten as A of W equals 80W minus 2W squared. Item number 2, complete the table of values on the side for the same function. A of W equals 80W minus 2W squared. You have 2 minutes. Go! Time is up. Look at the updated table of values and see if you got the correct answers. And showing this table to Mr. Santos could give him the idea that if he sets the width of the parking lot to 20 meters, then the parking lot would have the largest area possible. Kagamath, we have learned that in a quadratic function, the rule of the correspondence is a polynomial of degree 2. We have also learned how to model real-life situations using quadratic functions and how to construct a table of values to represent a quadratic function. In the next episode, we will be learning more. Until the next Mathathon, bye!